All right, this video starts part 2 of redox. So this is where we are going to start looking at using all the things we talked about in part 1 to actually start building some stuff, okay? So we are going to talk about two different types of cells when we are in this part of redox. We talk about voltaic cells and we talk about electrolytic cells. So if you remember back to the first part of redox, we talked about reactions as either being spontaneous or non-spontaneous. You're going to find that that corresponds to the type of cell we have. So a voltaic cell is going to be a spontaneous reaction, where an electrolytic cell is going to be a non-spontaneous reaction. The difference, though, between when we talked about it in the first part of the unit and when we're talking about it now, is we don't want the electrons to transfer directly from the metal to the solution or vice versa. We want to capture those electrons. So usually what we do is we maintain separation between the two different components that we have making up our cell. This way, we can connect them with a wire, and that wire is going to ensure that the electrons flow through the wire, and then we can capture them to do something useful, like light up a light bulb, power something, that type of thing, versus them moving directly from one thing to the other. So normally at this stage, we would spend some time doing a demo, and in class, we would spend some time building an entire cell. If you pause this video, I'm going to make sure that I also put a link on D2L, hopefully to a video that's going to do the same cell that I'm going to demo for you. So pause here, go ahead, watch that other video that shows you how to build that voltaic cell, and then you can come back to this one and we are going to look at what that's going to look like on an actual question, like how are we going to draw all of that out. Okay, so now that you've watched the video, let's have a look at how we would actually represent this in a diagram. So there are certain components to the diagram that are always going to be there. So the first starting point is to draw our beakers, right? You should have seen that she had two different beakers in that video. So we're going to draw two beakers next to each other. Okay, inside of those beakers, we had some solution, right? So we're going to draw little solution lines to show that they had some solution inside of them. Okay, generally when we create cells, we always want to use 1 molar solutions. Okay, the reason we want to use 1 molar solutions, if you look in your data booklet at that reduction table that we've talked about, you'll notice that there's a little star, and at the bottom under the table it says for 1 molar solutions. So once we start by drawing our two beakers, the next thing we're going to do is we need to indicate what we have inside of each of these solutions. So one of them was a 1 molar copper, let's just say it was sulfate, I can't remember exactly what it was. And then the other one, let me just make this font a little smaller so it actually fits in the beaker, because that's usually how we would do it. Keep going smaller. Apparently not small enough yet. Okay, let's try dropping a lot. Okay, there we go. Okay, the other one contained a 1 molar zinc sulfate solution. Same deal. We want to write that inside of the beaker. Okay, so we have our beakers. We've put solution lines. We have indicated what solution is inside of each beaker. The next thing to do is going to be to draw in those little electrodes that we had, right? So there was a solid strip of metal inside of this one, and a solid strip of metal also inside of this one, right? So if you think about when we talked about redox reactions in the first part of the unit, right, we talked about solutions and metal strips. Normally, we would have flipped it around, right? And we would have put like the copper strip into the zinc sulfate. But when we're creating voltaic cells, we always want to make it so that the metal strip is in the solution containing its own ion. Okay, why we do that is it's not going to react with itself. Okay, that's something hopefully you picked up in the first part of the unit, that generally they don't react with themselves. The only exception to that would be some of those transition metals that we had previously talked about, like chromium, iron, those types of things. Okay, so on your electrodes, you're going to write in what they are. So this one is copper, and this one is zinc. So we call these half cells. This is one half cell, and this is the other half cell. And why we call that? Well, when you take two halves and you put them together, you get an entire cell. Okay, if we think about the other components that were in the diagram, there was the wire, right? So we need to draw our wire, and that wire connected to our electrodes. Okay, then on that wire, we had a voltmeter. Okay, so generally we represent a voltmeter by a V with a circle around it. Try to draw a circle here. See how well my lovely circle goes. There we go. Okay, so that V with a circle represents a voltmeter. Anytime you see that there's a voltmeter, usually that's going to indicate to you that it's a voltaic cell, because it means that our cell is spontaneous and is going to be generating an electric current. Okay, so at the start of the video she had this, and you saw that there was no current being produced, right? There was no voltage being read on the voltmeter, and the current only started when we put in a salt bridge. So I'm going to draw a salt bridge. Normally you use a U-tube for this, called a U-tube because it kind of looks like an upside down U. Normally it's a little more curved on the ends, but my drawing with finger on trackpad is not so great, so I'm just going to use this function. Should extend that out a little more. No, didn't want to do that. There we go. Okay, so that's going to represent our salt bridge, right? And normally we kind of stuff the salt bridge with some kind of packing material. Usually we would use like cotton balls. We really just need enough of something so that we can fill the U-tube, cap the ends, and flip it over without all the solution come spilling out, okay? So generally in our salt bridge, there's a couple of different solutions that you could use. Often we use sodium sulfate. Okay, sodium nitrate is also sometimes used, and there are some other ones that can be used, okay? So this is kind of the general setup that every cell should have. Okay, so this is our starting point. Pretty much any cell question that's a voltaic cell is going to start with this type of setup. We're going to have the two beakers, we're going to have the electrodes, we are then going to have the wire connecting them, and then we are going to have our salt bridge, okay? So next thing to do is to start filling in some of these pieces. So what we need to do to be able to fill in these pieces is figure out what the reaction is actually going to be. So when we want to figure out what the reaction is going to be when we are in redox, remember the steps that we do is we list everything that we have. So normally we would know what we have because we would actually be in the lab, we would see all our solutions. In this case, we can figure out what we have just by looking at all the different solutions and items we've placed into our cell. Okay, so we're going to list everything we have, right? We're going to follow the same steps that we followed when we were in the first part of redox when we talked about writing equations, right? It was list, find the SOA, find the SRA. So let's start generating our list. So we have copper solid, right? Because that's our one electrode. We have zinc solid, because that's our other electrode. Within our salt bridge, we have sodium ions. We also have sulfate ions. Okay, and then within one beaker, we have copper ions. I don't need to write the sulfate again, I've already written that. And then in the other beaker, I have zinc ions. And then again,
you wanted a video of me and my new scooter.
Just a sec. Okay, and then not going to write the sulfate because I've already written the sulfate. Last thing I need to make sure I list is the water, right? We always got to make sure that we include the water. Okay, so now that we've generated our list, we need to assign things as being OAs or as being RAs. So copper solid over on the right hand side of the table, that means it's an RA. Okay, same thing for zinc. It's also on the right-hand side, so it is also an Ra. Okay, then we look for the sodium ion. It's way down near the bottom on the left-hand side. So that means it's an OA. Okay, sulfate, same thing. We find the sulfate a ways down the page on the bottom on the left-hand side. So it is also an OA. Okay, then we have the copper-2 ion. We find the copper-2, it's, I don't know, maybe a third of the way down the page on the left side, meaning it is an OA. Okay, well then we got to find the zinc. Well, the zinc 2+, I should say. Zinc 2+ is maybe a quarter up from the bottom, but also on the left side, so it is also going to be an OA. Then we have water, right? Hopefully by now you can remember that water can be both, right? It could be an Ra, or it could be an OA. So now that we've figured out all our potential OAs and RAs, we're going to go to our data booklet, and we are going to determine what is the strongest OA and what is the strongest RA. Okay, so for our OAs, we are deciding between a sodium ion, a sulfate ion, a copper-2 ion, a zinc-2 ion, or water. So we go to our data booklet. OAs are on the left-hand side. We're going to start at the top, and we are going to scan our way down until we find one. Okay, first one we find is right here. It's the copper. So we know that Cu2+ is going to be our SOA. Okay, so now that we have identified that Cu2+ is our SOA, we know what one of the half reactions is going to be, right? We know that whatever the SOA is, that's going to be my reduction half reaction. So because the copper ion is present in this beaker over here, we're going to write that half reaction underneath this beaker. So it was Cu2+ AQ plus 2 electrons to give us Cu solid. Okay, the other thing we're going to include that we didn't include when we were in the last unit is we're going to include that E0 value. So over here on this side of the table, you'll notice that it says electrical potential E0 in terms of volts. So we are going to record that value. So we look at copper, the E0 for it is positive 0.34 volts. So we're going to write down here that E0 equals positive 0.34 volts. Okay, so we know what half reaction is happening in this beaker. We need to go figure out what half reaction is happening in this beaker, okay? So we've identified the SOA. We now need to find the SRA. So we're deciding between copper, zinc, and water. So we go back to our data booklet. Remember, for RAs, we're going to start down at the bottom of the page on the right-hand side. So we start scanning. The first one we hit is the zinc. So that means that the zinc is going to be my SRA. Okay, so again, we're going to write that half reaction underneath this beaker where we have that zinc solid turning into a zinc 2+ plus 2 electrons. Okay, same deal. We want to go get that E0 value. Okay, that naught just means that it's at standard conditions. Okay, it doesn't really, I don't want to say it doesn't mean anything special. It does mean something special. But you'll find that when we do redox, it's always going to be E0. Okay, so for the zinc, it's negative 0.76. Ah, it didn't go where, whoa. Having trouble. So we said negative 0.76 volts, okay? Okay, so we've now identified what half reaction is happening inside of each of our containers. We also know what the E0 is for each one. So next thing we need to do is we need to identify which beaker has oxidation happening and which one has reduction happening. To do that, I look at my half reactions. So the copper, we have the electrons over here on the reactant side. So that means we have reduction happening on this side, which means we have oxidation happening over here, which we also can see from looking at our half reaction, right? We are losing electrons, therefore it is oxidation, okay? So the next thing we need to do is when it comes to our electrodes, so the electrodes are these solid strips, okay? So before I get to that, I'll put blank slide in with just a couple of things, right? So the purpose of an electrode is a solid surface where electron exchange can occur. Okay, and those of you that have taken physics, you're probably somewhat familiar with that term. So when we talk about electrodes, we have two electrodes. One of them is going to be the anode. The other one is the cathode. Okay, so the anode is the site where oxidation occurs. And the cathode is the site where reduction occurs. Okay, we often talk about little things to help you remember, and we tend to use a red cat to help you remember that reduction happens at the cathode. Okay, so red cat's going to help you remember that the cathode is the site where reduction occurs. Okay, we also have talked about Leo the lion says grr, right? So lost electrons oxidation, gain electrons reduction. Lots of little sayings to kind of help you remember things as you go. You'll also sometimes see that for anode, there's a an-ox, but I mean, I don't know. It just doesn't seem the same as a red cat, right? An-ox, kind of boring. Okay, so now that we know that, we've already identified that this is the beaker where reduction is happening, and this is the beaker where oxidation is happening. So from that, I should be able to recognize that because this is the beaker where reduction is happening, this copper strip is going to be my cathode. Okay, and then over here, because this is the beaker where oxidation is happening, this zinc strip is going to be my anode. Okay, so we will often ask you to identify what's the cathode, what's the anode. All right, next thing we need to be able to show is the charges, right? Think about when you use a regular battery, like a Duracell battery. It has a positive end and a negative end. Those correspond to the cathode and the anode. So what you find is that for a voltaic cell, the anode is going to have a negative charge, and the cathode is going to have a positive charge. Okay, and again, kind of help you remember that, we say cats have paws, right? So the cathode is going to be positive. All right, so from that, we should be able to go back here and figure out that because this is the anode, it is going to have a negative charge. Usually we do that and then we draw a little circle around it just to indicate what kind of charge it has. Okay, and then over on the other side, because it is the cathode, and the cathode is going to be positive, and same deal, we're going to draw a little circle around it. Okay, so we've indicated the anode, we've indicated the cathode. We made that decision based off of the half reaction that occurred in each beaker, which allowed for us to decide where reduction occurred and where oxidation occurred. All right, so next thing to show is the flow of our electrons, right? The electrons are flowing through the wire. They're either flowing from the copper to the zinc or from the zinc to the copper. How we decide which way they're flowing simply has to do with where is oxidation and where is reduction. Right? If you think about oxidation, it's defined as losing electrons. Reduction is defined as gaining electrons. So what that means is our electrons are going to be moving through the wire from the zinc to the copper, because they're always going to move from the anode to the cathode. So you can draw little arrows on your wire, and then we're going to indicate that that is the flow of electrons. Okay, so what you find, I'll add this to this slide here, is that electrons always flow from the anode to the cathode. Okay, and the reason for this is they're going from the site of oxidation to the site of reduction. Okay, So going back to our picture, because there's still actually quite a bit of information that we still need to show. So when she started building that Voltaic cell, initially nothing happened, right? This voltmeter was reading 0. It only actually started to read a number when she put the salt bridge into place. So why we need the salt bridge? We need to complete the circuit. Without the salt bridge, we don't have a complete circuit, right? We would have electrons wanting to flow this way, but then it would all stop, right? We've always talked about how charges have to be balanced. If our electrons are flowing and there isn't some other type of flow, there is going to be a charge imbalance. So this is why we need a salt bridge. Okay, what that salt bridge does, or the purpose of the salt bridge, so the salt bridge allows for electrolytic conduction, right? That's why we call it a salt bridge, because we put an ionic salt into it and it's able to conduct that electricity. Because it's able to conduct electricity, it's able to complete the circuit so that we have a complete flow of charge. Okay, the difference is what's moving through the salt bridge, right? Moving through the wire is our electrons moving charge, but moving through the salt bridge isn't actually electrons, right? It is those ions move, okay? So the ions move within the salt bridge to complete the circuit. Okay, so we have to show how those ions are going to move. Okay, so in our salt bridge, we had sodium ions and we had sulfate ions, right? So sodium ions are Na+, so they are cations. Sulfate ions have a negative charge, so they are anions. So sometimes you'll see it'll tell you what compound is in the salt bridge. Sometimes it'll just say like a plus charge and a minus charge, or a cation and an anion, and it's up to you to recognize which way they are going to flow. So which way they're going to flow basically comes down to what's happening to the charge in your beaker as that chemical reaction occurs. So if we think about this beaker over here of copper sulfate, before anything started, my charges were balanced, right? For every copper 2 ion, I had a sulfate 2- ion. So I had equal positive charges to negative charges. As this reaction occurs though, we're pulling copper 2 ions out of the solution and turning them into solid copper. So what's happening is the amount of positive charge within this beaker is dropping. The negative is staying the same because we haven't touched it, but the positive is dropping. And so what we're going to find happening is that our cation is going to migrate into that beaker to replace that missing positive charge and to rebalance out that positive to negative ratio, okay? So in this case, we can show that it's going to be the sodium part of this that is going to migrate this way in my salt bridge. Okay, then what we're going to find is over here in our other beaker, right, we had the same starting position where we had equal positive and negative charge because we had a 1-to-1 ratio between zinc ions and sulfate ions. But as this reaction occurs, solid zinc turns into zinc ions. So we're actually increasing the amount of positive charge inside of this beaker. We haven't changed the negative, but we've increased the positive. So what we find is because we have that imbalance in charge, where now we have more positive charge, it's going to be the negative, or the anion, that is going to be attracted into this beaker. Okay, so we always want to use arrows in our salt bridge to indicate the migration of those ions. Okay, in general, not in general, actually this is always true, you are going to find that cations always migrate to the cathode and anions always migrate to the anode. Okay, so we're always going to have that type of migration for our ions. All right, so now we've shown the migration of ions. The next step that we need to do is we need to indicate what's happening to the chemicals inside of each beaker. So to do that, we talk about the mass and we talk about concentrations. So I'm just going to change my colored pen because we're definitely getting a lot of writing going on in here and I want this to look a little different. So let's start over on the left-hand side with this beaker. So to begin with, we have solid copper, we have copper ions, and we have sulfate ions. So we need to discuss what's happening to all three of those species as this reaction occurs. How we discuss it or how we make that decision, we're going to look at what half reaction is happening in that beaker. That half reaction is going to tell me what my reactant is and what my product is. And in general, if you think about it, we use up reactants and we produce products. And if something isn't in this equation, then I'm not actually changing it. So, things we're going to talk about. We are going to talk about the mass of that solid copper. So when we look at the half reaction, solid copper is over here on the product side. So that means as this reaction occurs, I am producing more and more solid copper. That solid copper is all going to attach itself to this copper electrode. So what I'm going to find is that over time, the mass of my copper electrode is going to increase. Okay, because it was a product, I am producing it, so I'm going to have more of it. Okay, when we talk about what is in our solution, we had copper ions, so we're going to talk about as the concentration of copper ions. So when we look at this, the copper 2 was a reactant. Reactants get used up. So over time, I'm going to find that the concentration of that copper ion is going to decrease. Right? And if you think about it, copper ions are blue in color. So the longer I let this run, the lighter the color is going to become until basically it runs out and it's going to turn colorless. All right, last thing we need to talk about is the sulfate because it is also inside of that container. Okay, so the sulfate ion wasn't in our half reaction. That means the concentration of the sulfate is unchanged, right? We didn't touch it. It wasn't part of the reaction. So you're making the decision of what increases, decreases, or is unchanged based off of the half reaction you've written in your beaker. If something is a reactant in your half reaction, it is going to decrease. If something is a product, it's going to increase. If something is not in your half reaction, it is not going to change, okay? So we need to do the same thing over here in our zinc beaker. So same deal, we can talk about the mass of that zinc. So we look at our half reaction, the solid zinc was a reactant. That means that we are using it up. So what we're going to find is the mass of this is going to drop, right? And if you leave this long enough, you'll notice that it'll go from being a nice square and it'll start to become a little more like jagged looking because we're taking chunks of the solid off and they are going into the solution. Okay, concentration-wise, we can talk about the concentration of the zinc ion. Okay, and we're going to find that for the zinc ion, because it is a product, we are producing it, it is going to increase in concentration. Okay, last thing inside of that beaker is the sulfate ion. So we discussed the sulfate. Similar to the sulfate in the other beaker, it didn't change at all, right? And I know that because it wasn't in my equation. So this is also going to be unchanged. So you have to talk about the masses of the electrodes and you have to talk about the ions within the solution. So next thing we need to do is to actually generate a complete equation for this cell and determine what the theoretical voltage of this cell is going to be. So to generate the overall equation, we're going to take our two half reactions and we're going to combine them together to get that total. Just like in the last part of the unit, we have to make sure that our electrons are the same so that we can do this. We have 2 electrons and 2 electrons, so we don't need to multiply by any coefficients. So our overall reaction is going to be Cu2 plus Aq plus Zn solid to give us Cu solid plus that Zn2 plus Aq. All right, last thing we need to do is to determine what is the theoretical voltage of this cell? So we need to calculate the E naught of the cell. Okay, to be able to calculate the E naught of the cell, we always do the E naught of the cathode minus the E naught. Having issues here. Minus, there we go, E naught of the anode. So looking at what we have, we are going to have that the E naught of the cell is going to equal, all right, sorry, I'm having issues with my superscripts and subscripts. So the cathode, we look at our picture, the cathode was over here, it was the copper. So we are going to have that positive 0.34 volts, and we are going to subtract the E naught of the anode, which is negative 0.76 volts. Okay, so from here, we can determine what the E naught of the cell is going to be. So we do 0.34 minus negative 0.76, which winds up giving us positive 1.10 volts. Okay, really important to make sure you include the positive. I know in math you guys don't include positives, but when we are talking cells, we always want to either include the positive or the negative, because that sign gives us an indication of what type of cell it is. Okay, I also added a 0 off of what my calculator said because of significant digits. Right, you should find that every E naught cell you calculate goes to 2 decimal places. And that's because every single value in your data booklet also goes to 2 decimal places. Don't forget to put the voltage in as well. So, things you should notice. Anytime you are doing a voltaic cell, it should always have a positive E naught cell. Okay, so you can say voltaic cells always have a positive E naught. Okay, and that's because we're always going to have that situation where that OA is above that RA. Okay, and that's because voltaic cells are always going to be spontaneous. If ever you find that you've been asked to draw a voltaic cell and you've gotten a negative E naught, you've probably misidentified your SOA or your SRA. So important to try to go back and figure out where that's going to be. So voltaic cell questions are quite a bit of work, which is also why they're usually worth a lot of marks, right? So if we were actually in class and we were writing like a unit test or a quiz, or we were doing some of our voltaic cell labs, usually these questions are anywhere between like 12 and 13 marks, just because of how much work you actually have to do, right? We have to list everything, find the SOA, find the SRA, identify half reactions. We actually have to draw the cell. We have to identify oxidation, reduction, anode, cathode, electron flow, electrolyte flow, and then we have to talk about the masses, the concentrations, generate an overall equation, and determine the E naught cell, right? So a lot of stuff going into just one question. So most of the time when we build voltaic cells, we use the 2 separate beakers like you saw in that video. But sometimes instead we use a porous cup. So porous cup, kind of like the name suggests, is a little cup which has little pores in it. So you can use it in place of having 2 separate beakers. So generally what you would do in the case of a porous cup, okay, so this is basically what your porous cup looks like. It's a little cup, it's kind of like a, I don't want to say ceramic type material, ceramic isn't really porous, but you would pour your solution in. So instead of having 2 separate beakers, you're going to have 1 beaker, which you're going to put your solution in, but then instead of the second beaker, you're going to use the porous cup. You're going to pour the second solution into the porous cup. You would then put your electrode into the 1 beaker, and you would put the other electrode into the porous cup. You then would basically take this porous cup and stick it into the beaker. So when we use a porous cup, it's going to look like this, okay? So still going to have a wire connecting our two electrodes. Those electrodes are still going to pass through the voltmeter. But what you'll notice isn't in here is a salt bridge. Okay, the reason we don't need a salt bridge is this cup is porous, right? And porous usually means that it has pores that things can pass through. So what passes through this is our ions. Okay, we're going to find that instead of the ions migrating through the salt bridge, the ions are either going to migrate out of the cup, right? So they would go out of the cup into the solution, or they're going to migrate from the solution in the beaker into the cup, right? So if we look at this one, they're either going, not what I meant to do, they're either going that way into the cup or they're coming out of the cup. And what you find is it's still the same as before. The cations are going to migrate to the cathode, the anions are going to migrate to the anode. So if, let's say, this strip here is my cathode, it's the cations that are in this solution that are migrating in. And it would be the anions inside of the porous cup that are migrating out into the beaker. So what you find is we don't need that additional solution of that electrolytic solution because the electrolytes are provided from the solutions that we already have. So advantages of the porous cup, it takes less room, it requires less materials. Disadvantage, they tend to contaminate a lot faster because we do get those ions moving directly through, whereas we don't get that same level of contamination when we actually build those two separate cups. All right, so let's have a look at a couple of diploma questions. Okay, so I skipped the first one just because it's really a previous unit question, right? It's identifying OAs and RAs and what's stronger and what's weaker. And I really want to look at some stuff that's a little bit different. So here we have an electrochemical cell. I'm just going to pause because the recycle truck is going by. It's a little loud. Okay, so here we have this question. So if the electrochemical cell in the diagram above produces a flow of electrons in the direction indicated, then M and M2 plus could be. So we look at the pictures, we see that the flow of electrons is going from left to right. So what we need to be able to recognize from that is that electrons always flow from the anode, which is the site of oxidation, over to the cathode, which is the site of reduction. So why that's helpful is I know what one of these solutions is, right? I know one of my half reactions is going to have to be the cadmium with the cadmium 2 plus. And knowing that it has to be reduction is going to help me figure out what M and M2 plus are going to be. So if we find in our data booklet the cadmium undergoing reduction, right, we find right here is that half reaction. We're looking at reductions. So we have the CD2 plus 2 electrons turning into CD solid. Okay, so we know that here we have this. Sorry, I'm not including states right now, which really I should, but I'm not just because it's a multiple choice question. Okay, so we know that this is one of our half reactions. Why this is important is when I look at my data table and I find that CD right, oh, okay, that's some interesting highlighting, right here, I know this is a Voltaic cell. Why that matters is I know that this is a spontaneous reaction. So that means my OA, which is the CD2 plus, because that's the way this reaction is going, has to be higher than my RA. So basically the potentials for what the other thing is anything over on the right side that is below that cadmium reaction. So lithium, potassium, barium, calcium, sodium, magnesium, aluminum, and so on. So now when we go look at the list that we have iron, lead, nickel, and copper. We look here, the only one of those that's actually going to result in a spontaneous reaction is going to be the iron. Therefore, we know that the answer to this one has to be A. Okay, so next question. Which of the following equations represents the net reaction that occurs in the electrochemical cell? So any question like this, I'm not actually going to solve for you. I'm just going to quickly kind of walk you through what you would do because I want to try to keep this brief. Figure out what your SOA is, what your SRA is, and from there you should be able to generate that net reaction. Okay, the next one, what's the E0 cell? So same type of idea as the previous one. You need to figure out your SOA, your SRA. From there, you can figure out what your E0s are, and then you're going to do the cathode minus the anode, remembering that cathode is the reduction half reaction and anode is the oxidation. Okay, this one, which of the following statement applies to the operation of the electrochemical cell? So a precipitate forms on the zinc electrode, so that would be implying that that zinc electrode is increasing in mass, so you would have to look at what half reactions are occurring. The concentration of zinc ions decreases. Well, if the zinc reaction is Zn2+, turning into zinc solid, then that would happen, right? You'd have to figure that out. Electrons move through the connecting wire toward the zinc electrode. Again, all of this you would be able to determine once you identify your SOA and your SRA, which then lets you figure out what's the anode and what is the cathode. Okay, discharge. You guys often get thrown off by that word when you see it in these types of questions. So discharge basically means while a battery is producing a charge. So in other words, while it is running. Okay, so during discharge of the lead storage battery, blank move toward the cathode. So this is where you definitely have some memorization pieces, right? We talked about how the cations always migrate to the cathode, so we could get rid of A and B. And the species at the cathode blanks electrons. So again, this is also a memorization piece. We talked about the cathode being reduction. Reduction is defined as the gain of electrons, so we would be looking at D. Okay, so this one here, you're going to find your half reactions inside of your red book. You should then be able to calculate your E0 cell by doing the cathode minus the anode, okay? So this is basically how your Voltaic cells work. They are spontaneous. We are converting chemical energy into electrical energy. You're going to see when we talk about electrolytic cells, we're going to compare some things between them. You're going to find that some things are the same and some things are different.